Lecture, we're going to be talking about just some of the overall structure of the atmosphere, what it's made of, and so on. So this is the first lecture in our course, and it's based off of our textbook, pages 4 through 10. Well, let's jump in. So let's talk about what the atmosphere is. Now, the atmosphere is essentially one of several very important spheres, one of very important systems of our Earth. It's the air that's wrapped around our Earth. Without it, we wouldn't be able to live on here. So, thankfully, we have it. Now, how do we have an atmosphere? What gives us an atmosphere? Well, the same thing that keeps you and me bolted to the ground is the same thing that holds our atmosphere in place. It's gravity. So, because of gravity, our atmosphere doesn't fly off into space. And consequentially, gravity also keeps most of our molecules near the surface of the Earth. If you've never been to a high elevation region before, I'm sure that if you were to go up there, you would experience thinner air and be lightheaded. And a big part of that is because most of the atmosphere's molecules are near the surface of the Earth. As a matter of fact, even though our atmosphere is very thick, it's upwards of 300 miles thick, over 99% of the atmosphere's molecules are in the lowest 30 kilometers, which is approximately 20-ish miles. So think about that. Of our 300 plus mile thick atmosphere, almost all of the molecules are present in the lowest 30 kilometers. Now, with that said, even though our atmosphere seems like it's really thick, the reality is that it's not. It's a relatively thin atmosphere. We can see this by taking a look at the sunset from outer space. This image was taken from the Space Shuttle Atlantis as it had docked with the International Space Station. And it shows the sun setting. Everything up here is outer space. Everything down here is planet Earth. And this thin blue illuminated line is our atmosphere. So our atmosphere is actually very thin. And as I said, 99% of all the molecules lie within the first 30 kilometers. Most of us have a longer commute than that. So, yeah, our atmosphere is very thin. Now, it's essential for life on Earth. Obviously, it gives us the air to breathe, but it also does provide other really key roles, such as keeping us warm, allowing water to transfer from one location to another, and in fact, actually allowing water to be present on the Earth, and also helping to balance the Earth's unevenness. The atmosphere plays a key role in balancing our Earth's energy out. So the atmosphere has some pretty major roles that it plays, and this is just a handful. There are substantially more important roles that the Earth also, or that the atmosphere also plays in, such as the ozone layer and so on. Now, if I were to ask you, what's the most abundant gas in the atmosphere? You would probably think oxygen, right? Because it's what we breathe. Well, thankfully not, and there's a few reasons why. Oxygen is actually only the second most abundant gas. The most abundant gas, making up 78% of the air you and I are breathing right now, is nitrogen. And then another 21% is oxygen. That makes up 99% of what we're breathing right now. Simply between nitrogen and oxygen. That's unbelievable. Everything else in our atmosphere makes up approximately 1%. There's a little variation due to water vapor, but for the most part, it makes up just about 1%. The next most abundant gas is argon with 0.9%, and neon with 0.002%. These are called trace gases. But the reality is I really want you to focus on nitrogen and oxygen right now. Nitrogen makes up 78%, oxygen makes up 21%. Now, these concentrations remain pretty constant. However, there are some gases that can vary greatly from location to location and from time to time. Three key ones are water vapor, carbon dioxide, and methane. And we'll be talking about these a lot throughout the course of this class. So I'm not going to talk about them as much right now, but we'll be talking about them a lot. So if you were to take all of these gases and make a pie chart out of them, nitrogen takes up over 3/4 of that pie. Oxygen takes up another 21%, and then everything else in the atmosphere, substantially less. Now, those three trace gases I talked about a few minutes ago, those variable gases, water vapor, carbon dioxide, and methane, actually all have one very key role in our atmosphere. They're what are called greenhouse gases. Now, I know what you're thinking, and I've thought this as well, that greenhouse gases are bad, we need to get rid of them, we should hate them, and so on. But the reality is that greenhouse gases are actually our misunderstood friends. And I'll talk about why in a moment. The way greenhouse gases work, very similar to the windows in your car. They allow sunlight, energy, to pass through them. They're perfectly transparent to sunlight, the same way the windows on your car are perfectly transparent to visible light. However, they absorb other types of radiation that are trying to escape the Earth. So they actually trap that in. So they let energy in, but they don't necessarily let as much out. That keeps the Earth warm. So in a sense, they kind of act like a blanket in a way. And this is a good thing, because if we had no greenhouse gases, this average temperature of 59 degrees Fahrenheit would be substantially less. As a matter of fact, if we had no greenhouse gases at all, our Earth would be approximately 59 degrees colder than it is now. And there's a lot of implications to that. Different places would have different temperature changes and so on. But just to simply apply this, think about the temperature outside right now. Subtract 59 degrees from it. Regardless of how hot it is outside right now, that's probably pretty cold. That's probably pretty cold. So our world would be a much colder world, an unlivably cold world, if we didn't have any greenhouse gases. However, greenhouse gases also have an evil side to them. And the evil side comes from the old idea of too much of a good thing. The more greenhouse gases we have, the hotter our Earth becomes. And so as greenhouse gas concentrations are increasing, our Earth is responding by becoming hotter. We'll talk about that much more in detail later this quarter. But again, if we had no greenhouse gases whatsoever, the temperature outside would be, on average, 59 degrees colder. And we'll explain this image a little bit more later in this quarter. But just for right now, without greenhouse gases, the temperature outside would be approximately 59 degrees colder. Again, on average. So thankfully we have those greenhouse gases that keep some heat in, keep us nice and warm. Now, there are several key greenhouse gases in the atmosphere. Water vapor, carbon dioxide, methane, ozone, nitrous oxide, and I'm going to be breaking down each one of these throughout this quarter, but for now, let me just say that the two that we're most concerned about are carbon dioxide and methane. And the reason why is because water vapor cycles in and out pretty quickly. Ozone also cycles in and out of the atmosphere pretty quickly, as does nitrous oxide. These three greenhouse gases don't hang around as long as carbon dioxide and methane do. If we get one molecule of water vapor in the atmosphere, it quickly condenses into a cloud, rains back down, it's out. Ozone and nitrous oxide actually naturally cycle in and out of our atmosphere throughout the day. So, again, we're not as worried about those. Carbon dioxide and methane are the ones we're most concerned about. Now, of those two, however, carbon dioxide is the most concerning greenhouse gas. It's a byproduct of many different organic reactions, specifically burning organic materials. So burning wood releases greenhouse gases, any kind of fossil fuel burning releases greenhouse gases, and you and I are releasing greenhouse gases right now as we talk, because when we breathe in oxygen, we breathe out carbon dioxide. Now, carbon dioxide concentrations have risen substantially since the 1850s, and only a small portion of this has to do with more respiration, more breathing in and breathing out. Something else major happened in the mid-1800s. Those of you who are historians know that that was the Industrial Revolution. In the 1850s and, well, most of the 19th century as a whole, we realized that if we burn this stuff that we found in the ground, it created a lot of energy, and we could use that energy to fuel our cars, to move trains, to create factories. And we have developed as a society based on this. As a result, carbon dioxide concentrations have risen substantially. In 1850, they were approximately 280 parts per million. Now, they're actually over 400 parts per million. And we are adding an additional 3 to 4 parts per million every single year. So we're still increasing pretty rapidly year after year after year. Now, how do we know that this is happening? Well, one of the things we can look at are carbon dioxide measurements. And we have many different ways we can measure carbon dioxide. But over the last 60-ish years, we've had one location that has sort of become the standard location for measuring this stuff. And this location is on the big island of Hawaii, on a volcanic mountain 11,000 feet above the ground. 11,000 feet above the ground. And the reason why we care about that is because, the reason why we want it that high up is because it's away from urban influences, it's away from people, it's away from cities. And in case you're wondering what what influence the volcano has, the station is actually upwind of the volcano. So it never experiences volcanic effects, which is a good thing. But if you take a look, over the last approximately 60 years, carbon dioxide concentrations have been steadily rising. Again, from the late 1950s to now, they've been steadily rising. One thing you may notice is, while they're steadily rising, you actually do see a little bit of variation. Up, down, kind of like Bart Simpson's hair in a way. Well, the reason why this happens is because of seasonal variation. We all know that plants basically do the opposite of what we do. Plants breathe in carbon dioxide and exhale oxygen. Well, during the spring and summer months, there are more plants out. There's more plant activity, more photosynthesis, and as a result, carbon dioxide concentrations actually decline. On the other hand, in the fall and winter months, when we're all enjoying our pumpkin spice lattes and taking a look at all the leaves changing colors, those same trees are shutting down. And as a result, they're not taking in carbon dioxide. That causes carbon dioxide concentrations to go back up. So they go down in the spring and summer months, back up in the fall and winter months. And this happens on a yearly basis. But if you take a look, ignoring that pattern, you still see a very substantial increase in carbon dioxide concentrations just in the last 60 years. Now, if you want to take a look at the context of this, we have other methods of measuring carbon dioxide. And in fact, we can go back as far as thousands of years, using things such as ice core data, using things such as tree rings and seafloor sediment. And while they don't give us as broad a picture, they can still give us a pretty good idea of what's happening. And if you take a look, prior to Mauna Loa being set up, there was a relatively steady level of carbon dioxide concentrations. And then as we got into the 1800s, 1850s, there was a steady increase. But over the last 60-ish years, we've had a substantial increase in carbon dioxide concentrations. Now, the last thing I'll talk about for this little lecture is ozone. Now, we all know what ozone is, right? It's the thing that actually keeps us from burning. Ozone's a good thing because it actually keeps our skin from being affected by harmful ultraviolet radiation. But there is some ozone near the surface of the Earth. And it's a component of what's called photochemical smog. Basically, the way photochemical smog works is things shoot out of our tailpipes every morning, out of our car's tailpipes, and those things react with the sun, and one of the byproducts is ozone. But then again, ozone is a relatively unstable molecule, and it breaks apart easily. However, in the upper atmosphere, as I just mentioned, ozone is crucial to sustaining life. Why? Because it blocks those harmful UV radiation rays from coming down and cooking us. Now, just like ozone can form here near the surface of the Earth with sunlight, ozone can also form in the upper atmosphere in a pretty similar manner. You get oxygen molecules combining with rogue individual oxygen atoms, throw some sunlight into the mix, and voila, you've got ozone molecules. As I just mentioned, ozone absorbs that harmful ultraviolet radiation, protecting us. It protects us from what could really cook our skin. Now, ozone has had sort of an uphill battle over the past century. Over the past century, we as a society have developed something called refrigeration. And refrigeration allows us to keep our foods cool. It allows us to keep ourselves cool on hot days. And unfortunately, a lot of those things, a lot of those refrigeration processes involve the release of what are called CFCs, or chlorofluorocarbons. And these CFCs, once they get into the upper atmosphere, they actually have a pretty bad effect on ozone. They cause a decline in it. Now here's the good news. The good news is that we've actually, and I'll go back to this slide for a second. The good news is we as a world have actually all come together and said, no more CFCs. And we've reduced our CFC emissions, which is actually allowing our ozone layer to replenish. Again, ozone is important because it prevents the most harmful UV radiation, particularly UVB and UVC radiation, from coming down to the surface of the Earth and giving us bad sunburns, causing skin mutations, cancer, and things that would wreak havoc on humanity. Now, I'm sure some of you have heard about something called the ozone hole. Well, the ozone hole is actually a real thing, and it's present in the southern hemisphere, specifically near the South Pole. And the reason why it happens is because in their winter time, which is in their winter time, or the end of their winter time, which is the beginning of our fall time, the end of our summertime, beginning of our fall time, so the months of September and October, the air aloft above the surface of the Earth is really cold. And it creates what are called polar stratospheric clouds. These polar stratospheric clouds react with CFCs and cause ozone to deplete. Now the good news is this ozone hole is only present during a certain time of the year, specifically September and October, and it's been shrinking. And a big part of why it's been shrinking is because we've cut back on our CFCs. We've cut back on our CFCs. Now, just to review really quickly what we talked about in this lecture. First, the atmosphere is the envelope of air that surrounds the Earth. Greenhouse gases trap in heat, keeping the Earth warm. Ozone is the most important thing in the upper atmosphere. And this is obviously just a brief taste of what we've talked about. Now, in our next lecture, we're going to be talking about the layers of the atmosphere. The fact that just like our planet is split into different layers, crust, mantle, outer core, inner core, and so on, our atmosphere is split up into certain layers. Well, we'll talk about that next time. Till then, I'm Terrence Mullins. Thank you all for watching.